All right, welcome everyone to our next TCS Plus talk. And our speaker today is going to be Palak Jain, who is a PhD student in the computer science department at Boston University. Take it away, Palak.
Awesome. Thanks, Rachel. And I want to mention before I start that please interrupt me to ask questions if you have any questions. The way that I've planned the talk, I've left a ton of time for questions, and it's kind of aimed at answering questions. So yeah, I would love to hear questions if you have them. So I'm Palak. I'm a final year PhD student at Boston University, and I'm advised by professors Adam Smith and Mayank Varia. My work focuses on bringing robust data protections into practice through the lenses of cryptography, differential privacy, and machine learning. Today, I'll be talking about the enforcement of demographic coherence, and this is a harms-aware framework for reasoning about the privacy of large data releases. And I'm really excited to present this work today. It's joint with colleagues at BU, University of Maryland, and IBM.
FYI, Palak, we're not seeing your slides.
Oh,
They
let
appeared
me,
before and then they went away, so I assumed that you took them away on purpose.
got it. I will reshare. Thanks for letting me know. All right, is that working?
Yes, great.
Perfect. Okay, yeah, sorry. I'll just say kind of the project description again, since that wasn't up. So I'll be talking about the enforcement of demographic coherence, which is a harms-aware framework for reasoning about the privacy of large data releases. This research is joint with, oh no, I moved that over on accident, didn't I? This research is joint with colleagues at Boston University, University of Maryland, and IBM. So data plays a pretty key role in our society, whether it's census data being used for studying the migration patterns within America, or more questionably collected data like the driving patterns of anybody who drives a GM car being used for planning within the Department of Transportation. This large-scale collection and use of data warrants careful consideration about the potential for harms, which is a socio-technical conversation that's actively evolving today. And this conversation began with attacks, notably the famous attack by Latanya Sweeney, where she found and mailed Governor Weld's health records to his office. She did think that this attack was likely enough to succeed, and yet she found this experience to be an eye-popping experience. And in general, attacks play a very important role in the study of privacy protections in providing intuition and motivation. More recent examples include this study where researchers were able to re-identify a large percentage of trans kids in the US Census data from 2010. And that's data from before the use of differential privacy. They did this by comparing the gender of people in census data over time. So attacks, as I said, provide intuition and motivation for the development of formal privacy conditions, but they don't really directly provide a way to protect privacy. Meanwhile, defining a formal privacy condition is quite tricky. So motivated by her initial attack, Latanya Sweeney defined k-anonymity, but it unfortunately did not protect against re-identification in the way she was hoping it would. And so this led to the definition of L-diversity, which also didn't provide the guarantees it was hoping to provide. And kind of fast forwarding the story, a few definitions later, we got the definition of differential privacy, which is the accepted standard for privacy protection in many ways today. Differential privacy provides robust protection against worst-case adversaries, provably preventing the kind of attacks that we were talking about a minute ago. Yet the abstractness of this guarantee can make it hard to work with in practice. For example, the use of differential privacy for the 2020 census garnered significant criticism. The vocal criticism came largely from folks that believed the protections were too strong and the impact on usability was too large. But there's also a good number of people who believed that the protections provided were potentially too weak. So motivated by this backdrop, We introduced demographic coherence enforcement, which is a necessary condition for privacy, which is more concrete and can enable socio-technical conversations that bridge protocols, attack demonstrations, and formal guarantees. This framework, which is a harms-aware framework, takes into account the entire data pipeline and concretely models privacy loss via its effect on predictive harms. So it kind of intuitively captures these privacy concerns that we care about. It lends itself to experimental auditing in that there's a natural translation from the framework to an experiment for comparing different privacy-preserving techniques. And then the framework provably kind of prevents the types of attacks that the experiment would be about. The framework supports rigorous analytical arguments, which can be used to show that all differentially private algorithms enforce demographic coherence, which we do in our paper. And even though the direct use of this connection to differential privacy may not always be the best way to enforce demographic coherence, there is strong evidence to show that coherence enforcement is in fact achievable. And I'll discuss this more towards the end of my talk today. I know that there's a bunch of asterisks in this part, but I'll kind of explain all that as I get to it. So I'll start with the intuition behind our framework, and in particular, I'll talk about the importance of harm awareness. I'll also talk about the concrete adversarial model that we work in, and I'll give some intuition about measuring the possibility of harms. So just kind of to begin with, I'll say that our framework reasons about a data curator that takes in some data set XA and it produces a private report RA. And the framework is a way in which is a way to talk about how the data curator can limit the inferential harms that can occur as a result of the published report. So ignore the subscripts RA in this diagram for right now. They do become relevant later, and I'll explain them to you when they become relevant. So right now you can think of this as an input data of X and an output report R. So for most of the rest of the presentation, I'm going to anchor to this Netflix reconstruction example, and I will kind of slowly go through this example, and while I do that, I will also build our formal definition. And for those who don't know, the Netflix example is one where Netflix released a data set in, I think, 2006 for a competition for designing a better recommendation algorithm. And essentially, researchers were able to link the data in the Netflix data set to real people. So the data that Netflix published was anonymized data, so identifiers were removed, but these were able to be connected again. And the reason that the researchers were able to do this is because they had access to a very rich data set of IMDb reviews. And people that watch movies on Netflix, a lot of them also rate the same movies on IMDb. And as it turns out in this example, as in many others, the patterns in people's data are really fairly unique to the individual. So the patterns here would be the movies that people watch over time and how they rate them. And the question I'll kind of stop and ask here is, does the existence of this re-identification attack convince you that the leakage of this type of information is something that we should be really concerned about and something we should really protect against? And maybe it does, right? But for a lot of people, maybe it doesn't, because it's not clear the kind of harms that would be prevented from preventing this leakage. So maybe I can make this example a little bit more convincing by mentioning that there are movies that people watch and rate on Netflix that they specifically don't rate on IMDb for whatever reason, right? So if you compare the Netflix data to the IMDb data, not only can you figure out what their Netflix data is, but you can figure out exactly what they didn't want you to know. So that starts hopefully to be a little bit more convincing. And maybe I can make it even more convincing if I talk about a specific type of prediction. So for example, assume I'm in I'm a job candidate and I'm trying to get a job to work on something to do with like the newest Star Trek franchise stuff that's coming out, and I'm a diehard Star Wars fan, and I don't want them to know this because maybe they're going to think it's a conflict of interest and not hire me, right? And so I've taken a lot of effort to make sure that my public data doesn't reveal this. But if a company can create a predictor that allows them not to hire me purely due to the existence of this report RA, then perhaps it becomes a lot more convincing why we may want to protect against such data. So in general, when somebody, an adversarial actor, can confidently predict sensitive attributes of users, then things start to get a lot more convincing. And in particular, the point I'm trying to make here is that the value of privacy is tied pretty intrinsically to the harms that the data could cause to begin with. Right? So this means that a harms-aware approach really is crucial for intuition about privacy. Let me know if you have any questions, but I'm gonna keep going. So decisions that are made using predictions like the one I was talking about earlier are rampant in the real world, right? You know that our data is being used to impact our daily lives all the time. And the algorithms that power these predictions vary pretty widely from simple algorithms to opaque machine learning models. So the concrete adversarial model that we consider in our work is any adversary that kind of takes in this curated report and combines it with its own auxiliary information to produce a confidence-rated predictor. And just kind of to say a little bit about why we want to consider a confidence-rated predictor, if you take any complex prediction algorithm, this is kind of the simplest piece that could be distilled from any of them. So it's a broad way of talking about all these prediction algorithms. Now, focusing in on this predictor H, I will give you intuition about what we consider a bad or incoherent prediction. Let's assume that instead of just XA, we have a larger data set X that we can split randomly into two halves, where only one half is given to the curator and the other half is kept as a holdout. And so this is basically what the subscripts represent. Everything with a subscript A is based on dataset A. And now consider two people, Asahi and Blair, who are very similar. And the only difference between them is that Asahi is in XA while Blair is in XB. So I will discuss the potential privacy harms here. And what I'll do is I'll discuss two different predictors, and one will be more concerning than the other. I'll then show you later that the formal definition that we have really captures this difference and captures the type of harms that I'm discussing here. So, just going back to the example we had before, there's a company and it's hiring job candidates and it wants to figure out whether these job candidates have a conflict of interest. And its prediction on Blair is not sure, maybe not. Blair probably doesn't have a conflict of interest. Notice that if Asahi and Blair really are similar, then this prediction on Blair represents what the company can guess on both Asahi and Blair without having individual information about either of them. So a change in prediction on Asahi indicates a leakage of additional information about Asahi, right? Because the report was based on Asahi's data. So for this first predictor, maybe its prediction on Asahi is still pretty unsure, just like Blair, but it's an unsure yes instead of an unsure no. So this change in prediction, indicates some leakage of information, but let's consider a predictor H star, which we will say is more concerning. H star's prediction on Blair is still the same, so it's still pretty unsure and it's a no. But its prediction on acai is much more confident, and it's a confident yes, right? Then we can imagine that this is a scenario and this is a predictor, which is much more likely to end in acai being harmed, since the company is much more likely to rely on such a confident prediction to reject a candidate. So that points out that the confidence of the predictor really is critical. And so we do definitely want to measure that confidence. But also note that the company deciding not to hire acai based on this perceived conflict of interest has nothing to do with the ground truth about whether acai really has a conflict of interest, right? There's a harm-causing leakage here because the existence of the report drastically changes whether acai gets hired or not. And the truth of it really doesn't change that leakage. So the harms in experiment 2 don't depend on the accuracy of the prediction. So I'll use the intuition that I just gave you in this first part of my talk to flesh out our contributions a bit more. But first, I'm going to pause here in case you have any questions. Okay. So I already mentioned that our framework intuitively captures privacy concerns, but now I can tell you a little bit more about what that means. So in particular, our framework takes into account the entire data pipeline. It also ties to predictive harms, and this is what we mean when we say that it's a harms-aware framework. It has a concrete adversarial model, so you can really envision if you have an adversarial setting in mind and a type of harmful prediction in mind, you can kind of place that onto the framework to get intuition about it. And it evaluates risk without relying on ground truth. That is, it doesn't measure accuracy at any point. Finally, it allows the identification of effects local to specific vulnerable groups. And I'll get into what I mean by that last part right now. So consider some vulnerable group C belonging to this population, and let X restricted to C be this intersection of X and C. So let it be all the members of this protected group that are part of the data set X. Then, acai and Blair both belong to this group, and this is a way to talk about the similarity between acai and Blair. But acai is an XA restricted to C, while Blair is an XB restricted to C. So instead of looking at just like the predictions on individuals now, I'm going to think about the distribution of predictions on this group that I care about. So instead of looking at the prediction on acai, I'm going to think about the prediction on XA restricted to C. And this is because I don't want to kind of surface leakage about just individuals. The framework is trying to capture when there's systematic leakage of information about the people in the data set. So I'm going to consider the predictions of the predictor on either XA or XB restricted to this group that we care about. And formally, we're going to compare this distribution, which is the distribution where you pick a random element from the group, and like a random person from that half of the data set, and then you run the predictor on that person's data and see what it outputs. So that's going to define the distribution of predictions. And we'll say that the predictions are alpha incoherent with respect to the split XA and XB if the following holds, which is the difference between the predictions is pretty large. So let's look at these distributions a little bit to get a sense of how we measure this difference. Perhaps the distribution on Blair for both predictor HA and HA star looks something like this, which is that it's pretty unsure for most people and leans a little bit towards no. And this is for the people that belong to the same group subpopulation that we cared about, that Acai and Blair are from. And this is true for predictor H star as well. Now, I'm going to talk about how these predictions that we had of not sure, maybe yes, and almost definitely, what kind of distributions they could result in. So maybe the not sure yes distribution for this vulnerable group looks something like this for the people in XA, which is that, there's a little bit more weight on the unsure yes portion of the predictions. And on the other hand, when you have that very big shift in confidence, when, there were people that the predictor was unsure on, that, if they were in the data set that the report was based on, then the prediction is a much more confident yes. Then it may look something like this, where the mass has moved all the way over to the right from the middle. And so, the way that we define this, as I said earlier, is that the distance, the predictions are incoherent when the distance of the predictions between people not in the data set and people in the data set that was used for the report is pretty large. But notice that if I measured the distance between these distributions using the area between the curves, then you wouldn't really see the fact that predictor H star is much more concerning than predictor H. And so the way that we actually measure these differences is by using Wasserstein distance. And Wasserstein distance, which is known also as Earth movers distance, is much more suited to this task because it kind of defines the work that it would take to move from one of these distributions and deform it into the other. So if you kind of picture an ant moving grains of sand and a distribution is a pile of sand, then how much walking would the ant have to do back and forth to actually move all the grains of sand to form the new distribution? And so as you can imagine, this kind of surfaces the difference between these two predictors a lot better. So that's how we define incoherent predictions. And now we can kind of start to define what it means for a data curator to prevent this kind of prediction. So to, protect against these types of harms. And in particular, just focusing in on the data curator A, we will say that the data curator enforces alpha-beta demographic coherence with respect to some collection of subgroups that we care about and a size parameter gamma. If for all adversaries L, that is, the person on the right that was trying to make the predictions, all data sets X, and every, C, every group that is actually well represented in the data. So the size of X restricted to this vulnerable group is bigger than gamma. Then, so for every data set, every adversary, and every C, the following holds, which is the probability that the predictions are incoherent is pretty low. And what I mean by pretty low is that the probability is bounded by beta of incoherent predictions. And this probability is taken over the split XAXB as well as the coins of the algorithms L and A. So the coins of the data curator as well as the adversary. And I'll pause here to kind of give you some time to digest this definition. And let me know if you have questions about the example that I was talking about or the, any of the specific definitions or how it compares to things.
I have a question, and this may be coming later, and so if that's the case, feel free to tell me to wait. Is this looks a whole lot like a calibration or like a multi-calibration. Can you talk about that, or will you later, and then I will wait?
So it does look a lot like multi-calibration, mostly in that we're measuring this value over all this entire collection of subpopulations, but we don't actually explore formal connections between multi-calibration and this framework. But it is literature that we took inspiration from, so that's why the similarity does exist.
And
Yeah.
can you also point out some of the like key technical nuances as to why this is not multi-calibration and sort of like where are the points where this definition diverges from that one?
This is a good question. I'm trying to remember what the multi-calibration. Can you remind me what the measurement is in the multi-calibration definition again? I'm trying to.
Actually, that's a part of what I was hoping you might remember because I also don't know it off the top of my
Ah,
head. Yeah,
that's
like
fair. Maybe we can get. Yeah. No, go for it.
okay,
What were you
sure,
saying?
sure. If it isn't immediate, then that's fine. Whatever
Yeah.
you say.
Yeah. Um, the yeah, one of the things that comes up a lot is the connection of this to perfect generalization. So I kind of have that a little bit more immediate, but I'll
Oh yeah.
definitely let you know about the multi-calibration one soon.
Okay.
Some of the things to notice about the definition, one of the things to notice is this data set split. So one of the choices you could make is to actually have IID data sets pulled from the population, and then you give these to the data curator. But we choose to do the data set split because we want the experimental framework where you might test for attacks actually leads back to the definition, and the definition just directly protects against the types of attacks that you'd be surfacing in the experiment. And in practice, people usually use a data set split in half rather than, two IID data sets because you
Yeah.
can't really do that. Yeah. So that's one of the things that is interesting here. And I'll kind of move forward, but let me know if you have questions about any of this, and I'll be happy to come back. Right now, I'll actually go through the list of stuff that I said our definition satisfies, and I'll talk through what that means. So we say that the definition intuitively captures privacy concerns, right? So I said it takes into account the entire data pipeline. And what I mean by that is, some of these things that I was mentioning. So we split the data set instead of sampling two data sets. We also actually have the entire data pipeline as part of the framework, as opposed to something like differential privacy, which is a lot more abstract, where, all these things are kind of, it's maybe cleaner to write down, but you can't quite map a pipeline that you have in your head as easily onto the framework. Next, it ties to predictive harms, and by that I mean that we kind of really focus in on these confidence-rated predictors and the fact that they allow you to think intuitively about the types of harms you care about. It has a concrete adversarial model, which is this adversary that produces a confidence-rated predictor. It evaluates risk without relying on ground truth. So there's no point in this framework where we measure accuracy. And that was actually really important to us when doing this, because like I mentioned earlier, the actual kind of, there could be a leakage even when you don't make accurate predictions. And moreover, there may be a lot of scenarios where the ground truth isn't even available, right? So when we have census data, what is ground truth for that data set? We don't really know. Finally, it allows for the identification of effects local to specific vulnerable subgroups. And what I mean by this is if you say you have a data user that you're talking to and they have an idea of the vulnerable group that they care about, and they can describe the groups to you, and what you can do is you can put this group into the definition, right? And what you would do is you would check that the size parameter, right? So the amount, the representation of this group in the data set is actually large enough for the definition to apply. And so you can kind of, for example, a while ago, I was talking to somebody from like the city of Boston, and their goal was to place resources for specific marginalized communities in Boston. And so if I were implementing demographic coherence, I could give him a good idea of whether the protections would apply to the communities he specifically cares about. Moreover, to provide more intuition, I could have run an experiment where I concretely compare the existing algorithm to the algorithm that I'm maybe want to implement and show him the Wasserstein distances specific to the groups that he cares about. So that's what I mean by the framework lends itself to experimental auditing, is that you can run an experiment like this and give a really good intuition to data users that you're talking about, and maybe even get some kind of heuristic understanding of what's going on. So what you would do is you'd pick a specific data set, you'd pick maybe some adversary that you consider to be convincing, and then you can swap out the data curator with the privacy preserving techniques that you want to compare. So finally, I'll talk about the last two things that I mentioned, which is the fact that the framework supports rigorous analytical arguments, in that all differentially private algorithms enforce demographic coherence, and we're able to show this because of this property, and some proof that this definition is achievable. Before I do that, I'll mention a little bit about related work. And so there's kind of two main lines of work that are related to the work that I've been presenting today. And the first one is there are some works already that define necessary conditions. And these necessary conditions are essentially in the form of protection against specific types of attacks. So there are a couple papers that defined protection against reconstruction attacks in particular. And there was another paper more recently that defined protection against, it defined a framework where you could then have specific definitions that were specific to different attacks, like reconstruction attacks and singling out attacks, etc. So the necessary conditions in these papers are formalizations of a different kind of privacy guarantee, and it's a different type of necessary condition than what we consider. And, you know, depending on the actual scenario that you're in, it may actually make sense to consider a set of necessary conditions rather than just one. So that's necessary conditions. And on the privacy auditing side, there are some papers in the area that classify attacks on practical systems to help determine realistic threats to a system. And there are others that kind of focus only on auditing differential privacy parameter settings, and they do this through attacks. However, the connection between these two spaces for differential privacy are not direct, right? These are usually focused pretty heavily on differential privacy, and the framework that we define lends itself to both auditing as well as, you know, comparing different pets in a way that makes it clear that the framework directly prevents all the attacks being considered. So finally, I'm going to tell you a little bit about the fact that differential privacy also implies coherence enforcement. And specifically, the theorem says that if an algorithm is epsilon differentially private, then it also enforces alpha beta demographic coherence under this condition that alpha and beta fall in ranges that would allow this inequality to be true. The actual kind of constant K is spelled out in the theorem in our paper. I just left it out of the slide for just like clarity. And essentially what the theorem is saying is that differential privacy implies coherence enforcement. The other direction, though, does not hold. So coherence enforcement does not imply differential privacy. And how can we see this? So there's a very simple algorithm that is coherence enforcing and does not kind of satisfy differential privacy, that kind of feels intuitively like it does not kind of have leakage, right? So if you have some sort of binary vote, say, you know, you're deciding on, I don't know, whether we should ever order pizza for seminar talks ever again or not, because somebody really doesn't want pizza for seminar talks. You can take all these votes, and if you strip all the auxiliary information and just post a list of all the votes and this kind of just the binary bits without the ordering, without any of the other auxiliary information, then this is coherence enforcing. And this kind of makes intuitive sense, right? Because we don't actually expect that the results of a vote themselves are kind of non-private, at least like they don't systematically leak information about the individuals that were in the vote. And demographic coherence in this way kind of surfaces the benefits of data minimization, right? Such a algorithm that doesn't have any randomness cannot satisfy differential privacy, because a differentially private algorithm that is actually based on the data does have to use some randomness. And so, these things combined actually give pretty good evidence that we could, achieve coherence enforcement in the way that we define in our paper. So for certain settings, and, if your groups of people that you care about are pretty large as well, like say like a tenth of the data set, something like that, then you can use the theorem that I have on the top of the slide directly to, use differentially private algorithms to get coherence enforcement. But there's actually evidence that you can do better, right? If differential privacy really does, coherence enforcement really does surface the benefits of data minimization, we should be able to combine techniques of data minimization with, maybe some noise addition techniques from differential privacy to get even better algorithms. And that actually brings me to talking about, future work. So one of the things that would be really exciting is thinking about algorithms that satisfy this definition. And there's, good evidence that you can do that. And, maybe we can use other tools as well, perhaps, thinking about the connections to multi-calibration, maybe boosting algorithms can satisfy this sort of guarantee as well. The other thing to really think about is composition. So this is really helpful when building complex systems. But the question for this framework is, how do we define composition? Because if we're thinking about, two different data curation processes and they're run on two different data sets, especially two related data sets, then how do we define composition? Because the data split in the beginning of this framework kind of causes a little bit of trouble there. And even if we do once we do define what we mean by composition, there's a chance that composition holds, but there's also a chance that it doesn't. And in that case, it would be interesting to explore whether there are weaker composition guarantees that might hold. Like if we kind of combine a coherence enforcing algorithm with a differentially private one for the same data set, do we, end up with something that's still coherence enforcing? And finally, I want to mention experimental auditing would be really interesting for this line of work, because you could kind of experimentally try to distinguish obviously bad algorithms from ones that we trust, or kind of go back to like actually really working with somebody who wants to implement a system and compare different things that could be used and see how they do to get a heuristic understanding of what's going on. Yeah, so that's our framework of demographic coherence enforcement, a harms-aware framework for reasoning about the privacy impact of data release. I do have, I can talk a little bit more about the comparison to generalization if people are curious, but yeah, I'll open the floor here for questions.
Thank you, Palak.
Thank you so much.
And I'll let you field your own questions.
I can't see if there are questions in the chat. Should I?
There's no questions in the chat. If there are any, I can read them out to you. And for those in the audience, feel free to either type your questions in the chat or jump in. Again, like it will be a question period after the recording ends, and so if you feel more comfortable holding your question until then, that's totally fine. I have a question to start us off. I was really interested in this example you gave of your recent conversation of a like a city employee trying to like protect a certain group and sort of how these results apply. Can you say more about like specifically how these results could be used in a setting like that? And is it like theoretical one could, or is it like no, they're definitely ready to go? And if it is theoretical, what are some like barriers that you think exist into like bringing this like theory result into practice?
So I'll go back to the slide just so we have the framework diagram up here. And for that example, thinking about census data especially, there's actually, you could really use the definition that the kind of theorem that we have showing that differentially private algorithms enforce demographic coherence to potentially get something that is usable in that setting that has enough privacy and still preserves utility to a big extent, because the parameter conversions there possibly work out pretty well. I didn't actually, so this conversation that I had was a little bit before we actually came up with the framework. So there isn't an actual kind of process that we went through where we use this framework with this person from the city of Boston. But the way in which I would really picture using this framework in that discussion would be twofold. So one of them, that discussion really got stuck on, so the person said, okay, I have a sense of, you want to use differential privacy in the census. I have a sense of the kind of harms that could cause, right? I want to place these resources for groups that I care about, and it will make it impossible for me to see the exact kind of location information that I want. What are the harms that it will prevent that you can talk about? And so in that situation, you can actually kind of go through and, if they can talk about some of the harms they might be worried about with respect to privacy leakage, you can actually place them in the framework and talk about how the framework would or would not prevent these harms. Whereas with differential privacy, we kind of got stuck on the like membership inference point, because it is kind of an abstract definition. And so he was kind of saying that, why do we care about membership inference for the census, right? Everybody supposedly participates in the census. This is not the thing that we should be worried about. And so that's one use case. But the other thing that I think would be really interesting is kind of using the fact that you can really swap out the data curator here and still measure how the predictor does. So once you have some specific attack, you can measure how it does on all these different privacy preserving techniques, when you use all these different privacy preserving techniques for the report, and you can actually compare them in a way that connects to the property that you would be providing if you implemented the algorithm that you were talking about. And so I think that would also really add to the intuition, especially if the data user you're talking to comes in with suggestions about what they would like to do instead of the framework that you want to use.
Thank you. Any other questions in the audience?
Hi, Palak. I have a question.
Yeah.
Hey, maybe you could talk more about the difference, the difference in flavor between other kind of proposals that have been advanced as sort of necessary conditions, which, as you say, kind of correspond to attacks. And like, what do you think of as sort of being qualitatively different about the kind of approach you're taking? Which I agree.
Right. Yeah. So for some of the other papers that focus on attacks, they focus, for example, in the narcissist paper, they have a definition called narcissist singling out. And this really focuses on being able to single out individuals, right? But because of the kind of property we're trying to capture just systematic leakage of information about the data set. And we do this kind of distributional comparison. And the distributional comparison we do would definitely not kind of point out singling out, for example. And so that's one of the differences. But also kind of when it comes to things like reconstruction attacks, they're a different type of guarantee than these kind of more basic confidence rated predictors, like general confidence rated predictors. Yeah.
Thanks.
And a lot of the a lot of the related work in general that I mentioned here and that exists, that I mentioned, there's a lot more in the paper, focuses on accuracy quite a bit for auditing and for kind of checking attacks and this sort of thing. And so that's one big difference.
Any more questions? Don't be shy. Okay, in this case, let's thank Pollock again, and I will end the recording, and then we can ask all of our secret questions. Thank you, Pollock. Excellent talk.
Thank you so much.